Yes, so today we have the pleasure to welcome Feldbrugge, who is visiting from Edinburgh University. So Jaap has been working on many topics, including cosmic web, but also up to quantum cosmology and various topics between students. So today we'll talk about caustics, but in case you're interested in something else, I'm pretty sure you can come to our office and talk to him. He will be there today, this afternoon, for instance, too, so don't hesitate.
Thank you very much for the invitation to give this talk. It has been a great joy to join you for a week here. And I will be talking about the cosmic web. And it will be a little bit of a theoretical talk, but I'm very happy that the formalism is now getting ready to actually be applied in embodied simulations. And also we can start to think about how this can be used to study, for example, galaxy formations. So even if you are not very involved in the cosmic web, you might still learn something, and you might still get a feeling for how we can use the cosmic web in astronomy in general. So this is work I've been doing with Rien van der Wijngaard, who is in Groningen, and my PhD students, Benjamin Hatch and Mari Rodriguez. And I'm just very happy to show this, and let me know if there's anything unclear. We have to mute. Yes, I already missed. All right, so what we have in the cosmic web, in cosmology, later cosmology in general, is that we have observations of the time fluctuations, of the temperature fluctuations or density fluctuations at the time of recombination, when the universe turned neutral and gravity starts to become important. So you could say that's kind of the advent of astronomy, because there gravity becomes a major player instead of the electric forces, for example. And this is something we can understand very well because it's completely described by a power spectrum. So assuming it's a Gaussian field, and we know it's very close to a Gaussian field, we have a lot of control over its description. However, these fluctuations gravitationally evolve into the cosmic web, which we see today, which is this highly complicated structure consisting of dense clusters, long filaments, thin walls, and voids, of course. And this is a very non-Gaussian structure. And what I will be talking about is a formalism by which we can map the initial conditions to the geometry of the final conditions. By fundamental language, we can systematically study this in new ways, which I hope to show you during this talk. So the main question I will be answering here is what makes a wall, what makes a filament in terms of the initial conditions? How can we predict which regions in the initial condition are the proto-walls, the proto-filaments, and the proto-clusters? Of course, if we run an embodied simulation on such a Gaussian field, and we start from very blurry noise, it's a little bit like the noise you see in your television screen, old-fashioned television screen. But if you now turn gravity on, and you see that there is this formation of this cosmic web, what you see is that our first filaments start to form in isolated patches, and then they connect up to form this beautiful geometric pattern, which we see in the embodied simulations, but also see in the sky. So certainly with Daisy recently, we have been seeing this.
So this is pure dark matter, or is dark?
This is just dark matter. And my whole talk will be just on dark matter, but has applications to baryonic matter. But this is just to show how this forms. And the question is, how can we understand how this geometric pattern arises? And can we use that in a systematic way so that we can ask more questions and probe deeper questions? So again, we have observations, like, for example, the Sloan observations, and we have simulations, like, for example, the Millennium simulation. We see statistically kind of the same pattern, we see this web-like structure. But so far, it has been very difficult to quantify this from first principle, to say, really, this is the geometric shape we expect from first principle from the initial conditions. That's what I will be talking about. All right, so as we know, the universe is expanding. So since Einstein, we know that we are having a dynamic space-time. We have a Big Bang or a bound or something. It could be inflation, or it could be some other process as an early universe. When the universe expands, it cools down, and at some time point, it becomes neutral. Then gravity kicks in, and what we will talk is about this part of the evolution, where you start from the Gaussian field, and you end up with the universe today. That's what we will be describing. Of course, the homogeneous, the zero-mode evolution of the universe is described in terms of the Friedmann equations, which is a special case of the Einstein field equation. This is kind of a homogeneous universe, but what we will be doing, we will be looking at observations in this universe. So at the CMB, this is a Gaussian field. might have learned about it at some point. But basically what you do is you say, I have a power spectrum, or I have a 2-point correlation function. And this completely describes this object, which is a Gaussian random field, which basically says, if I take a function out of a set of functions, let's say the probability that my function is an element of some set of functions, and the probability for that set is given by an integral, which is really a path integral over a form which is e to the power minus something like the action, where the action is a quadratic form. So this is basically saying the Gaussian random field is a stochastic object, and this is a realization of that object. So this is an example of a typical Gaussian random field which you would expect. And this is what we model the initial conditions, the CMB with, and that then leads to the formation of structure. These are the initial conditions. Then we have the evolution of these initial conditions in this expanding space-time. So what we have, of course, is a conservation of force with the Euler equation, which is force is mass times acceleration in a set. And you have the Poisson equation, because the force is governed by the gravitational potential. So you have the density field, which sources the gravitational potential. You take the gradient of the gravitational potential to calculate the force, and the force pushes the particles around, subject to the conservation of mass, because we're assuming that no mass is lost or added to the structure. And this is one way of viewing this. It's known as Eulerian fluid dynamics. What I'm talking here about is the Lagrangian perspective of things. And this sounds like a crazy way of approaching it, but it's actually very close to what we do in embodied simulations. What we will be talking about here is Lagrangian fluid dynamics, and it's simply saying the positions of the mass elements of the universe, the position of the embodied particles in your simulation, they are the fundamental property, the quantity which we are tracking. So what we say is, well, we say that the point which started at Q at the time of the CMB, the initial conditions, is mapped to xt in the current universe. And what you do is you say, well, that's really the initial position plus the displacement. So let's say you woke up this morning in your bed, and that's your initial position, Q. And you say, well, you moved by amount S to arrive in this auditorium, for example. If you can track the evolution of all the particles in your fluid, you are all-knowing, because you can subsequently derive the density field, for example. So you can say the density of your fluid at time t is given by one over the Jacobian. So this is just like what you learned in integration theory. If you do a change of coordinates, then you have to compensate by the Jacobian, which basically gives you the volume of your squeezing or compression of your fluids, which is given like this. It's a little bit more complicated because this mapping is not one-to-one. So you see that you really have the sum of all the particles which maps to this Eulerian position. So if you say, I would like to calculate the density field at point X, then you have to take the inverse of this mapping. You find the Q's which map to that point X. And each of these Q points in the initial conditions give you a contribution to this density field, which is of this form. Again, the equation of motion for this X variable follows from the Euler equation and the Poisson equation. And what we will do in effect here is we will use the Zeldovich approximation. So what we will do is we will often use just a linear approximation to these equations of motion for X. And what you obtain is that the mapping is indeed the final position of a particle, starting at Q is Q plus S, displacement, so there's nothing new here. But what you do is you say, well, my displacement field is really minus the growing mode, which is a temporal function going from 0 to 1 from the time of recombination to today, or the Big Bang to today, times a gradient of a potential field. And this potential field is related to the primordial gravitational potential. So the Zeldovich approximation is very simple. What you do is you say, I take my primordial density fluctuation, I calculate the associated gravitational potential. Now I get the gradient of this gravitational potential, and that basically tells you how the particles start to move. What we will just do is we will keep them on that path. It's a ballistic motion. It doesn't turn around. It's very unknowing of the evolution subsequently. And that's what is the Zeldovich approximation. And this is typically used to set up embodied simulations because that allows you to do the first step in your evolution. Here I will take it seriously up to the current time. So that's a little bit different from what you would expect. So the spatial information in the Held-Orbit approximations is captured by the primordial gravitational field, which is a Gaussian. And the time evolution is given by this equation of motion, which is basically just a time parameter for structure formation. And that's basically the framework within which I will work. So what you can do is you can take an embodied simulation, that's on the right. You can take the Held-Orbit approximation, here is on the left. You see that at early times it works very well, but at late times the Held-Orbit approximation completely fails. That's also what you would expect. If you now look at the density field, which is given by this formula we just talked about, so it's the sum of all the particles which map to X prime. So you take the inverse, the pre-image, and you sum over all these particles, and then for each of the particles, you are basically calculating how much that mass element has stretched or squeezed. It's just a consequence of the conservation of mass. And what you find is that you find this determinant, and now you can calculate the density field in your embodied simulation. So I've taken a three-dimensional embodied simulation, I take a slice through it in a plane, and calculate the density field there.
It's just the test domain. You might do it twice.
All right. So what you do is you calculate the density field, and you see the cosmic web emerging. So you see a more advanced cluster-like region here. You see that it's really forming this structures. You see here a sheet, which is a multi-image region, as we will see, meaning that this sum actually consists of multiple points which map to the final condition. And you see that it's a very sharp transition from, let's say, a void-like region to a filament or a hole. What you really see is here the emergence of caustics. So what you can do is you can calculate the density fields, like I did here, and this is done using.
Sorry, just to understand.
Yes, please.
The void is really empty here.
Yes.
I guess there is a criterion that you define to say there is a light, I mean, in the image to say there is something or not something, because there are galaxies in voids also.
Yes, but this is a very poor embodied simulation. So it's only dark matter at the moment. It's really it's 100 megaparsec with 512 non-every axis, so it doesn't have a resolution to recover the galaxies in the void.
Okay.
Just to make sure I follow, the equation you show here allows you to compute the density field at the current day based only on the disposition of the particles at the initial conditions.
Yes. So this is an embodied simulation, so it is not a simulation. So you start with the initial conditions and you run your embodied simulation.
It's incredible you get to bypass everything in between. And
no, I'm not bypassing anything. So I'm not using the Held-Orbit approximation. So it's not this equation. It's solving this numerically.
Okay.
So it's just solving, in effect, these equations numerically. But if you do it and you calculate the density field, you see that there are these regions where you have multiple streams. So these sum consists multiple images. Here you see how many images there are. So you see that the geometry of the cosmic web is nicely traced by the multi-image regions or the multi-stream regions in cosmology. So what you really see here is the formation of caustics. So you start from a mass fluid which is one-to-one everywhere, which is kind of smooth. And then what you see is that as gravity acts, particles are moving, and you get a multi-stream region, which immediately means that if you project it down, you have multiple images. So here you see that there is a three-image region or a three-stream region. And here you see a one-stream region. And you see at the boundary, you find something which is known as shell crossing, which is a caustic. And that's in particular the fold caustic. But in addition, you find that there's this cusp, the point where this fold caustic pinches off. And that's known as a cusp caustic. And there is a whole classification of these caustics, which is known as catastrophe theory, developed by René Thom, and that's what
it's known as
catastrophe theory.
Okay.
What you're presenting here is, let's say, a dense region in the center and particles flowing on both sides on it, right?
Exactly.
But you showed it as a 3D. Well, it was just to.
It's just an illustration. It's nothing.
It's really flowing thus.
This catastrophe theory really already emerges when you have projections of manifolds to lower dimensional spaces, and that's just an illustration. But the same phenomenon is leading to these very sharp transitions from the single stream region to the three-stream region, because what you find is that this density spikes at this transition. So in order to go from a single stream region to a three-stream region, you will find that the determinant becomes 0. And that, of course, you divide by 0, so you get a spike in the density field. That's really the marker here. So as I said,
Can I ask us?
yes, please.
What is a Feldbrugge pancake?
So the Feldbrugge pancake is basically the high dimensional version of this. I can show you an animation. So what you can do is you can you can consider this same kind of picture where mass has turned inside out. You have developed this multi-scene region. If you now in 3D color in the places which are shell crossing, and that's the blue here, there's a kink around it, which is a caustic. So what you find is that you get the geometric shape, which is a little bit like this. So it's like a saucer. So you see that you have this, which we call the Feldbrugge pancake.
Okay.
And that's again bounded. So here you have the single stream region, here you have the 3-stream region, and the boundary is given by this shell crossing region, which is the fault caustic, with this rim, which is the caustic. So let's go back. So the beauty is that all these singularities in these mappings can be classified with catastrophic theory. So what you can do is you can say, well, let's take a step back. Let's forget about all the gravitational physics. And let's say, well, okay, we have this dark matter sheet in the initial condition, which is basically just a plane. And it gets folded due to gravity somehow. And what we're doing is we say we don't care about the folding, we care about the density fields today at the current universe, which is in effect a projection procedure. What you can have is, for example, this yellow manifold in 3D. If you project it down to the 2D plane by removing the z direction, then what you will find is that here this point leads to a single stream region because there's only one point in the z direction above it. But here you find that you have 3 solutions, so you have a 3-stream region. And the 3-stream region is separated from the single stream region by the place where this manifold falls over. That's known as the fault caustic. And that gives you this black line. And what catastrophic theory tells you is that there's only a finite number of ways in which you can stably develop these singularities in these mappings. So in this case, this line is the fault caustic, which is given by this one. In addition, you see that there is this pinch point here, which is a higher order caustic, which corresponds to the cusp, which is this one here. And depending on the dimension of your space and your manifolds and your mappings, you can have a finite set of ways in which you can develop these caustics. And that's given by the 7 elementary catastrophes, which are given by this one. So you have the old, you have the cusp, you have the swallowtail, you have the butterfly, and in addition, you have 3 more, which are the umbilic caustics. And that's it. So this is actually an extension of the critical points which you learned about in school. So you have critical points, which is a function, the gradient is 0. Normally you use the Hessian to determine whether it's a maximum, a minimum, or cell point. But if the determinant is actually 0, then the classification splits up into these 7 catastrophes up to the dimension of lambda and x. This is the mathematics which I will leverage to understand the cosmic web. Questions? Yes.
And so typically all the mathematical forms.
They knew we were talking about catastrophe.
Yeah.
In case of catastrophe, you get this.
We'll get a lot more of that.
And so all this mathematical form for caustic, then physically the form of the caustic will depend on the galaxies that live inside because it's like physically all the characteristics then depend on the
Keeps trying the same thing for 10 times. At some stage, he has to understand it works.
I was wondering how is it related physically to the distribution?
So this folding really works on a large range of scales. But what I will talk about is only its application to the cosmic web. So then it really tells you what makes a ball, what makes a filament, what makes a cluster. That's because I will use this adoptive approximation. But in principle, you could dream about applying this to the displacement field in general, and then you can try to say, is there a distinction between clusters, which would be then kind of the group of galaxies, which are butterfly or parabolic caustics? But that's at the moment something I can only dream about. It's not something which is being worked out.
Okay, and I was wondering also, this caustic is like under the Zeldovich approximation?
No, it's zero.
Here and not here.
So I will apply it to the Zeldovich approximation, but the classification of caustics is fully general.
Okay.
So for any x like this, you can have a mapping from Lagrangian space to Eulerian space, from Q to X space, and the density field arises due to this formula, which is basically a projection formula, and for that kind of mathematics, catasticity theory applies. So it's just like this same things happen in optics. So optics and geometry and body simulations have one thing in common. It's displacement of particles. It's displacement of light rays, so to say. For that kind of mathematics, this classification applies. So I will apply it only to the Zeldovich approximation, but that's kind of a baby version of the more general theory, in a sense.
Just to make sure I understand, you use this because in the formula of the density field, you need projection effects that are explained by this theory. Okay. So the places where you have these free streams, is it where you observe filaments physically?
Yes,
okay.
clusters and walls.
All right, okay.
And absence would be a void, so to say. All right, so let's take a step back and let's see this in action. So this is again this two-dimensional and simulation, and what you see is the formation of clusters. You see the formation of filaments, and since it's 2D, you don't have walls. But the main point I would like to capture is that if you would only know the multi-stream regions, know the boundary between the single-stream regions and the multi-stream regions, then you already have a nice probe on the geometry of the cosmic web. So what you see is that initially you have no multi-stream regions. Over time, the first multi-stream regions form. This is kind of the two-dimensional representative of the Zeldovich pancake, if you will. And then subsequently, they form this whole interconnected web, which is what we see in the sky.
Just to understand,
Yes.
It's not scale invariant, or it's like there is a specific scale that emerges, no? Or...
Well, this is a very poor two-dimensional and body simulation with a power spectrum, which is nothing like the scale invariant power spectrum.
Okay.
So it's just to illustrate.
Okay,
It's also only two-dimensional. So it's just,
But of course, there is a scale. It's
Yes.
like M star. It's a formation structure.
And that scale is that emerges there is the one that we observe.
It's just a growth of the cosmic web. So it's a scale of the
Well, it's of course it's not
spectral mass.
but
This is an simulation of the cosmic web. So
He said this is
well,
so something is talking about three-dimensional and some simulation. I was talking about is two-dimensional.
Is it just a way to describe like the filaments, just a redefinition in a sense?
No, I'm just questioning naively even the 3D simulation in the sense that the contrast here is extremely fine.
Yes.
And I always remember this comment of Peebles about these simulations and comparing them to the actual 3D distribution of galaxies and saying that the voids are not as empty. I mean, are very empty, and it's not that easy to clean the voids. Here we have the impression that it's clean.
But the power spectrum I've used here it doesn't have anything on small scales. So this is not to be trusted for these kind of questions. So the only point I was trying to make is that you have this folding in phase space, which leads to these multi-stream regions, which can be tracked by the caustics. So I'm basically just trying to match up the algebra which I showed a second ago in the geometry.
I mean, you're lucky because you never get that many essays. That means it's an exceptional moment.
So this is not something which is new. So Arnold and Zeldovich in the Russian School of Logical Structure, which is basically...
So Arnold is Russian also?
Yeah.
Okay.
Yeah, well, he studied at some point. He worked after the fall, the Soviet Union, he worked in France, but
Okay,
The
I
original
don't
is
know.
correct.
Yeah.
But Vladimir Arnold, who you probably have learned about from Hamiltonian mechanics, he's done many fields. He said always that mathematics is just a very cheap laboratory for physicists. So he used his mathematics in order to study the cosmic web at some point, but then he moved on and he did all kinds of other things. So Arnold was basically refining René Thom's catastrophe theory at the time. And Zeldovich was describing his Zeldovich approximation, and they were friends, so they met up. And they worked together with Sergei Shomharin, who unfortunately passed away this year, and we know very well in the large-scale structure community. And they were trying to use this mathematics of catastrophe theory to classify the cosmic web. Because at that time, we didn't have reliable embodied simulations like we have today. So they needed mathematics to understand what these embodied simulations would give. So they wrote this part 1 paper, which was on the 2-dimensional models, and they write that they would like to write part 2, which would be the 3-dimensional universe, but they couldn't do it at the time. And that's what I will be talking about. So what you can do is you can set this mapping from Lagrangian space to Eulerian space. You have this displacement map, you have this density fields. You find that the density field spikes when 1 plus the eigenvalue is 0, where mu is eigenvalue of the deformation tensor, which is the gradient of this S vector. So to just wrap up, you take this gradient of S, you calculate the eigenvalues, and then you see, well, if 1 plus mu is 0, then I spike. So that leads to a spike in the density field. But if you would like to go higher in catastrophe theory and consider the higher order caustics, then you have to do a little bit more, and we will see that the eigenvectors, which are typically ignored, will play a major role. So what you can do is you can say, let's consider Lagrangian space, which is the space of initial conditions. Let's have this general map, and it's not Zeldovich approximation, it's just fully general Lagrangian fluid dynamics. You have this map X, which maps any point in this space to a space in the current universe, current configuration of particles. What you now can do is you can draw in any manifold in Lagrangian space. So let's say this red curve is an example of a manifold. You can map all the points which build up this manifold to Eulerian space. And what you will see is that if you have a manifold here, it's no longer a manifold typically here. And develop these kinks where the tangent space is not locally defined. And that is basically to understand these caustics. So what you can do is you can say, well, what are the properties of this manifold and the mapping from Lagrangian to Eulerian space, which lead to such a discontinuity, such a kink in the curve? And if you work on this carefully, it took me 3 years to figure this out because you try different formulations and many things don't work. But in the end, it leads to a very simple formula because you say 1 plus the eigenvalue field. So that's no surprise because we saw already that 1 plus the eigenvalue field appears here. Times the dual of the eigenvector fields. So these are the active eigenvectors we talked about a second ago. And the tangent of the manifold in the point, that has to be 0. All your dimensions. So I goes from 1, 2, and 3 in 3-dimensional web, 1 and 2 if you have a 2-dimensional model. So now you know how such a singularity occurs. If you now apply this to the whole of Lagrangian space, then what you will find is that 1 plus mu is 0 leads to the first order caustic. That's a Shelperson beat, and that's what we already knew. That's when the density field spikes because one of these products in the denominator was 0. However, if we now apply the same condition to this manifold, so now the red line in the previous plot is this manifold, then what you will find is the cusp manifold, which has to satisfy this condition. But in addition, you find that the directional derivative of the eigenvalue field in the direction of the eigenvector field has to vanish. And that is the condition at which you have discussed, which was this discontinuity in the folded manifold. If you now repeat this process and you go to smaller dimensions, then you can basically derive a condition for the fold, cusp, swallowtail, and the butterfly caustic. So these are the same caustics we saw from the classification, which were already known from René Thom and then Arnold. But now we have it in terms of local conditions on the displacement map, because you see it's all in terms of the eigenvalues and the eigenvector fields of the deformation tensor, the deformation tensor of the gradient of the displacement map. In addition to these A caustics, we have 2D caustics. So this D4 is very easy to see because you see that both 1 plus mu1 and 1 plus mu2 has to be 0. So now you have not that the denominator is 0 due to one eigenvalue field, but 2 simultaneously. And this is again a part of catastrophe theory, which was already known. But now we have very concrete algebraic relations which classify them. So if we now apply this to, let's say, the Zeldovich approximation, then we get these singularities of different dimensions. And we can say, well, the cusp singularity leads to a two-dimensional manifold of singularities, ergo it's a wall. The swallowtail caustic leads to a line-like object, ergo it's a filament. The butterfly leads to points singularities, which would then cluster. Similarly, you find that the D4 caustic, which is the place where two of these eigenvalue fields are blowing up simultaneously, if you shoot curves, which would then correspond to filaments, and the D5s correspond to clusters. So if you apply this now to the Zeldovich approximation, you have a way in which you can classify the initial conditions of the cosmic web, and you can build this embryonic skeleton of the cosmic web.
I'm so sorry. When you were trying to pass from one space to the other, deriving the conditions on the eigenvalues, that was passing from Lagrangian to Eulerian space?
Yes.
Okay, that was not from like initial conditions to present day.
That's Eulerian space is the present day, and Lagrangian space is the early universe. Right. So just different terms for the same object.
I didn't understand the difference between the A and the D classes.
So the A caustics are really related to one eigenvalue field. So let's say lambda 1 or mu 1. The D caustics emerge due to two eigenvalue fields. So you see that this 1 plus mu 1 and 1 plus mu 2 is 0. So it's basically saying if we have the density formula, then you can have a singularity, a blow up due to only one eigenvalue field, or you can have a blow up due to two.
Physically, it changes if you have one or two.
Yes. So that will lead to different formation channels, which lead to different filaments. And ultimately, my hope is that that leads to different local environments of the cosmic web, which then also would source different galaxies. That's what we are working towards. But it's a first principled machinery, so you start from nothing, you have to build it up slowly. So the prediction from catastrophe theory is that you actually do have two different filament types. And in both simulations, we see that these form earlier, they are longer, they are thinner, and these are forming later, they're thicker, and they are more heavy. And if you do a first order approximation, you see also that the density profiles are different at them. So this is just a result of symplectic geometry, so you shouldn't take it too seriously because embodied simulations are very nonlinear. And we are normally looking at it at large scales. These relations will fill, but you see that there's a difference. So I hope if there's a difference already at the linear level, then we expect that the still to persist at the nonlinear level. So it's all very nice that you can do this algebra, but what does it give you? So one thing is very simple. You say, well, eigenvalues apparently play a big role. So let's take a Gaussian random field, which is this blob-like pattern, which is representing the primordial density field. We can now calculate the gravitational potential associated to it, which is just an inverse Laplace transform. It's still a Gaussian random field. At every point here, you can take the Hessian, and that's still a Gaussian random field. Now you can calculate the eigenvalues of these Hessian. This is just a two-dimensional example. So we have a 2 by 2 matrix, which is symmetric. There's two eigenvalues, two eigenvectors. Here you plot the eigenvalues, the first and the second eigenvalue field, and the eigenvectors associated to it. What you see is that this is a very non-Gaussian object. You see all these worms in the initial conditions. These are the proto-walls or proto-filaments in this model. So this is already showing that you can already see the structure today in the initial conditions once you use the right mathematics. So let's take again this embodied simulation and the Zeldovich. What I will do is I will calculate the caustics in the initial conditions of this Zeldovich approximation, and I will map them on top of this embodied simulation. What you can do is you can take the eigenvalue field, which is the green here, which is this worm-like pattern. You can draw in all these caustics, which we have now derived in terms of these algebraic conditions. So you have the fold caustic, which are isocontours of the eigenvalue field, which are in red. But then you have the cusp caustics, which are the blue lines, let's say here. If you take this skeleton, so the red lines and the blue lines, and you map them to today, to Eulerian space, from Lagrangian space to Eulerian space, and overlay them with cosmic web, you see that everywhere by eye you would have identified, oh, that's a filament construction. You see and the caustic. Of course, this is just 2D, and it's for a power spectrum, which is very simple, but in principle, you see that there is some merit to it. Why do we expect this to actually work? Well, these caustics really mark the place where the Zeldovich approximation is failing, because the Zeldovich approximation exactly fails at the event of multi-stream regions. And the subsequent gravitational evolution basically phase mixes and virializes the objects around it, but it doesn't really displaces it very much. That's the reason why you can use the high order caustics of the Zeldovich approximation to predict the geometry of the cosmic web today. You can do this in 2D. You can also do it in 3D. So then you should think about the Zeldovich pancake, which we were just talking about. And what you can do is you can take a three-dimensional Gaussian random fields. You can calculate these caustics, and you can overlay them with the embodied simulation. You see that initially you have something which is very Gaussian, and you have only a few Zeldovich pancakes, which then extend over time, and they map up to form this fully interconnected, like Swiss cheese kind of structure with bells and foam bubbles in it, which gives you the boundary between the different voids. You find there are the filaments which are here displayed in blue. You can do this again in embodied simulation. So here you see the representation of the filaments of the A type, so the swallowtail filaments, and in red you see the umbilic filaments. So you see that they're correlated, but they are not the same. So it's nice that you can now visualize this, and you can see that everywhere where you would identify a geometric structure in the cosmic web, you see that there is this, which is in this case the cusp sheet going through it. So it's a mathematical way of describing the geometry of the cosmic web. And it's nice that you can make this, do this and make this comparison, because the formalism here, which I use, is based on the Zeldovich approximation. We are comparing it to the fully nonlinear embodied simulations. So here again, we have a slice of the density fields, which we saw before. You see these caustics. So everywhere you see a spike in the density, say, aha, that must be a shell-causing region. That's what we just learned. We can overlay the caustic skeleton through it. So this, the red is the walls, because you take a three-dimensional simulation, you slice it through a plane, so you get a constant curve. And you see the blue points are actually the filaments. We have the filaments of blue and green, which are the A force and the D force. You see that it nicely tracks the geometry of the density field today. So we have some handle on what the proto-walls and the proto-filaments are from the initial conditions, based only on local analysis of the initial conditions using the Zeldovich approximation. When I show this, people say, oh, but you're missing a lot of structure. You see a lot of filamentary region here, or whether it's a wall of filament, it's difficult to say from a two-dimensional slice. But what you can do is you can say, well, let's not cut the skeleton off at the current time, so the mass elements which have shell cross today, but let's extend it also into the future, and then you get this. So the different colors gives you basically the amount of time we look into the future, and you see that basically all the structure up to megaparsec scales is captured by these caustics, which is just a set of nonlinear local conditions on the gravitational potential at the time of the CMB, which I find really exciting. So when I first started this, I didn't dream that it would work up to megaparsec scales. I thought this will work for the largest, but my PC shouldn't just run it, and it seems to work. So at some point it will fail, because this, we are assuming the Zeldovich approximation, but apparently it's still a very powerful method to understand the cosmic web. So you can do it also in scale space. We were talking about scales a second ago. So typically what we do is we say, well, observations won't be sensitive to all the structure of the cosmic web. So it's nice to have a hierarchy, because it's a hierarchical structure. It's like fractal objects, is a CMB in a sense. So you expect walls to be composed out of smaller walls and smaller filaments. So what you can do is you can take your primordial density field, you smooth it, we do it with the Gaussian, and you can look at how the caustic skeleton evolves as you increase the smoothing. So this is very little smoothing, so sigma 0.5, and we slowly increase the smoothing. You see that, for example, here this arm extended a little bit further. If we go further in the smoothing, you see that at some point you are only sensitive to the most massive walls in this case. So this is a way in which we can split the structure apart into the most massive objects and the more fine-grained details. We can also compare it to the halos. It's a very poor embodied simulation, so you shouldn't expect the halos to be in the voids. But still, what we find is that if you take a wall-like region like here, you find that the halos are forming strings within this wall. If you now overlay the caustic skeleton with it, you see that the halos are really tracking the swallowtail caustic within the wall. So this is kind of the first order approximation of the bias, because you see where do the galaxies or the halos form within the cosmic web. And they are not forming at random locations, they are really forming at the locations which you can predict using these caustics. So when I did this first, I thought that the full small scale case within my walls must be noise, because there are so many numerical steps.
I have a naive question.
Please.
When we compare the caustics or the large scale structures to the observed universe, the only thing we see in the observed universe are
Yes, yes.
and so fortunately they have to match at some stage. But here they don't match so perfectly.
Yeah, that's because I take a two-dimensional slice.
Okay, it's a projectile effect.
If you want to do it in 3D, then you find that they are really nicely overlaying the cosmic structure. So you can say, oh, what is this? Well, that's just because of this is an infinitely thin slice.
Yeah.
But in order to have actually street-type structure and has halos, because there will not be no halos if you make the slice infinitely thin.
Yeah.
But it's difficult to show that in 3D on a.
Okay.
To tell you that that's where you have to trust me. Yeah, so that's something we're really excited about, and we would like to study it further with more detailed embodied simulations, which are, for example, also can include baryons. And we can really see to what extent that works. But you would expect that the different locations, environment in the cosmic web, to classified using these caustics, have local different behavior. So you have, for example, galaxies and voids, which are very different from galaxies in clusters. But now you can do that more in a refined fashion.
I'm very sorry to come out each time because I just tell you that our speaker for this afternoon, Mr. Train, I have to cancel the whole thing, but I'm listening. I'm so sorry.
All right. Yes.
I'm sorry, can I ask a question?
Please.
On different parts. I kind of lost the idea of what the Zeldovich approximation was and why it's useful.
So the Zeldovich approximation just takes the primordial gravitational potential, we scales it by a number, take the gradient everywhere, and that's the direction in which the particles start to flow when gravity becomes important. The Zeldovich approximation just continues that motion. So it's a linear extrapolation. So it's linear first order Lagrangian perturbation theory, and then.
So do you end up using it because you showed at first that it doesn't really match?
Yes.
Like,
so it doesn't work for the A2 folds. The shell crossing regions are completely irreversible. It turns out that the higher order caustics are still informative. So even though if you look at the density field within Zeldovich approximation and the body simulation, say this is nonsense, it doesn't make any sense. If you look at caustics, then it still has a lot of information about the nonlinear gravitational evolution of cosmic wave.
Right.
Okay. Can I summarize this in another way? Because I had difficulty to understand how you use the Zeldovich approximation to actually do a statement on the embodied simulation. What you say is, if you know the displacement field at initial time,
yes,
you can just map the higher order caustics and guess where are going to be the structure in the embodied simulations, because it's just this first order that is going to localize where these structures are, and then you can just know where they are and try to study them in the embodied simulation.
So, but it's really a mathematical language that I've been developing to have a way to track the geometry of the cosmic web from first principle without having any assumptions, because these singularities are just given by catastrophe theory. So it's not like you have to trust me to have a good judgment for what a filament or a wall is. It's just what comes out of the formation history. So in the last few minutes, I would like to show you something which is making this more practical. So we can talk about the skeleton of the cosmic web, but of course we would like to see how the galaxies are behaving and how the different density fields are looking. So what we can do is we can do constraint simulations using constraint Gaussian field. So as I said before, a Gaussian field is just a statistical object, which is kind of like, if you're in field theory, it's Euclidean scalar field theory. It's only kind of a kinetic term because you have just a quadratic term here. And this K is kernel, which is fully described using the power spectrum. So that's very clean and simple. If you say, I would like to impose constraints, and you have linear constraints, then the situation is very simple. So this is known as the Bertschinger-Hoffmann-Riebuck algorithm. So if you go to Wikipedia, you look at a multi-normal distribution, and you can see that if you have a two-dimensional Gaussian distribution given by the mean and the covariance matrix, and you impose a linear constraint, x2 is a, which is just some number, then you can show that the conditional distribution is given again by a Gaussian, and one-dimensional Gaussian, where in this case the mean is given by this formula, and the covariance matrix is given by this formula. And the Hofmann-Riebuck algorithm, or the Bertschinger-Hofmann-Riebuck algorithm, what it does is it makes use of the fact that though the mean depends on the value A, the covariance matrix doesn't. So what you can do is you can take an unconstrained Gaussian random field, you can basically measure the A, you can subtract the mean using this formula, and then you can add it to the mean field of the thing you would like to impose your constraint on. And that's how you generate these very efficiently. But this is really relying on the fact that this is a linear condition. Because these conditions on terms of the eigenvalue fields are hardly linear. So what we have been doing is we have been extending constraint Gaussian random field theory to nonlinear constraints. Where you can consider the space of linear statistics on which your nonlinear constraints depend. And here it will be the Taylor series of the gravitational potential to a certain order. And you can impose the caustic conditions, which are these conditions in terms of the eigenvalues and eigenvector fields. You can sample that using this probability distribution, and we use some Hamiltonian Monte Carlo sampling to do that. And it's a rather low dimensional space, so that goes really quick. And then you can import them into the Hofmann-Riebuck algorithm, which is this kind of systematic way of generating initial conditions. So you basically extend your Taylor series to the whole box, and then you can sample these constraints. So what you now can do is you can start with these kind of conditions, these conditions which follow from catastrophe theory. You can imprint them on your initial conditions, and you can grow the universe with that condition. So this way you can generate, let's say, a wall with a certain length scale forming at a certain formation time. And you can see what the morphology is in the current universe. So you can look at how the galaxies behave or the halos behave around these different walls. So I tried this for the first time, and it didn't work at all, because the points which I constrained were more in clusters than in walls. What we basically found is that you have to add a second set of conditions. You have to say, I don't want to be on an arbitrary point on these curves. I would like to be in this region where the particles are stretching away. Because if the particles are moving towards the cluster, then you are more likely to end up in the cluster. If we take these maximal stretch conditions, which is basically these conditions, which are again fully local conditions on the gravitational potential, in addition to the caustic conditions, then you will generate your filaments or the walls. So what you then can do is you can run a set of embodied simulations, and you can track where the particle where you suppose to constraint lives. You see that it's every time at the center of this box, you see there's a nice filamentary region which is sticking upwards. So we have managed to run simulations which are realizing the caustics from the Zeldovich approximation in the embodied simulation. We can now look at what the statistical properties are as a function of formation time, the time of shell costing, whether it's a very old filament which formed at a very early time, or whether it's a filament which just formed yesterday. And they will have different properties. So this way we can split it out. You also would expect that if you have a galaxy which forms next to a wall which forms very recently, it will be different from a galaxy which would form at a wall which was forming very early, because it is for a longer time exposed to the nonlinear gravitational evolution around these walls. But it's nice to do this in 2D. How do you generalize this to 3D? That's always the goal. So we had before these caustic conditions for the cusp walls, swallowtail filaments, and the umbilic filaments, which were given by these formulas. We now say we would like to be at the center of the wall, or the center of the filament, which is maximally stretching outwards. And what we obtain is that we have to add these additional conditions for the wall, these for the swallowtail filaments, and these for the umbilic filaments. And once you impose these conditions, you have a fully nonlinear set of conditions on the Taylor series, basically, or the germ, if you want, of your gravitational potential in the initial conditions, and then you can run these constraint simulations, and you can see what actually the morphology and the properties of the cosmic web. So it's like you are a doctor and you're not treating the whole body. You're saying today we'll look at the lungs, tomorrow I will consider a leg. And that's what we have been doing. So if we impose a cusp constraint in the center of the wall in the blue point, and run the embodied simulation, you see here in the density fields, you see a planar structure, because in one axis it's like a pancake. And the other axis, it's like a line, so that's really a wall-like structure. You see that it's away from the filamentary regions, which are really on the outside. If you look at this in the flip-flop fields, it's just looking at the multi-stream regions. You see that this is again showing, so you see that there's a filamentary region around it, but blue point is not in the filament because you want to be out at maximal stretch, which is imposed by these conditions. And you can see it in slices, but you can also see it in this animation. So the white point is where we set a constraint. The red is the custom manifold. And you see that it's nicely inside of this structure, and you can study now these walls very systematically. You can do it for the walls, you can also do it for the filaments. This is a swallowtail filament, which is again the white dot in the center. And you see that there will be clusters above and below. This is really a part of the filament which is maximally stretching. You can do it also for the umbilic filaments, which is here the green line, which will be a more massive filament, forming again due to a different formation channel. And we are currently in the process of seeing what the statistical properties of these filaments are in the embodied simulations. I hope that will come out later this year or early next year. So we can really use this formalism to do play God in a sense. We can do the same thing chemists do or biologists do. They go into the wild, they find a specimen, and they put it on a petri dish, and then they grow it and see what happens. We can take this mathematics in combination with the Zeldovich approximation. We can identify the derivatives which leads to a proto-wall, a proto-filament, or proto-cluster. We can grow it in our embodied simulation and can see what actually happens. And this is, as far as I know, the first way we can do this really from first principle without assuming some general properties which are ad hoc. So it's really due to this falling in the phase space. So you can do it for the walls, you can do it for the filaments. So here you see in particular the green filament, which is the umbilic filament, the swallowtail filament, and the blue filament, which is the umbilic filament. So you see that they are related and calculate the correlation function between them using the initial conditions. And that's something we still have to do. But you at least now have the toolkit to ask these questions and try to formulate a solution in a first principled way. So with that, I would like to conclude. So I hope to have shown you that you can track the geometry of the cosmic web from first principle by tracking the folding in phase space and using this mathematics which has been developed in the last century, which is known as catastrophe theory. And in the 80s, people in the Soviet Union could dream about how it works, but they had some mathematical hurdles to overcome. And over the last few years, I've been really dedicated to overcome these hurdles so that we can now run these embodied simulations and we can basically reunite this initial approach to understand what's happening without embodied simulations with the embodied simulation we have today. Because I think the combination will give you a very strong toolkit to study the cosmic web in new ways. And I hope that ultimately this will help our understanding of for example, the alignment of galaxies with the cosmic web or even galaxy formation, because if you have a different local environment, you will also expect the galaxies different morphologies. But one of the things we are currently doing is we are applying this, for example, to the multiple simulations. So these are reconstructed initial conditions for a local universe. And there we have an embodied simulation which basically results into the distribution of galaxies in our local environment, our cosmological backyard. And then we are looking at how does this structure form? Which elements of the local universe forms first, which form later? What are the properties of the galaxies in real surface compared to the caustics we predict here? Because there is one big weak spot in this whole formalism, is that we classify the different elements of the cosmic web based on their formation history. But we observe only the current distribution of galaxies. So you have to do an additional step in order to remedy that. So one way is to use these constrained initial conditions, which, for example, we're using the Borg reconstructions, or you can also use Hestia or any reconstruction of the initial conditions. So that we are very lucky that this is now already around the time that these reconstructions become more adept. Another thing which we are currently doing is we are trying to train a machine learning environment to recognize these structures from the current distribution of particles in surface, because we can run these constraint simulations, which can be very small and local, and they can basically serve as a training set. So it's like you have a lot of pictures of people, you say, oh, these are faces, and this is a face of a woman, this is a face of a man, this is a face of a child. Can you identify these faces and can you estimate what the age of the person is or what the sex of the person is? And that's something we can also do here, because we can run simulations and we can teach the machine learning algorithm what the cosmic web looks like and how a filament which forms early differentiates from a filament which forms late. And we can try to see whether we can apply this, for example, to Daisy or Euclid. So it's something I'm very active at the moment in exploring.
Just on the specific point that you're studying the evolution of, the growth rate of the filaments depends. Would you gain by, let's say, using a Euclid in 3 slices in time as a better probe of the model rather than just one single snapshot?
Yes, for sure.
Okay.
Because you would expect that the properties are different at different times. And you can predict that already from the initial conditions. So you might be familiar with Rice formula, which is a way of doing stochastic geometry on Gaussian random fields. You can now extend that to all these different elements of the cosmic web, because the whole idea is that we have a mapping between the late time universe and the initial conditions. Because in the initial condition, we know all the statistical properties, and in the late time universe, it's very complicated.
Yeah.
But this caustics theory allows you to model the nonlinear behavior of the cosmic field. So I hope that this will be complementary to two-point correlation functions, which are amazing, but they also are summary statistics, and they are collapsing a lot of data into a single curve. So if you can complement that with the geometry of the cosmic web, which we know includes information which are lost in two-point correlation function. Yes. Two-point correlation function is assuming that cosmic web is a Gaussian random field, for instance. I hope that this will be a powerful way to keep track of that. Also, if you know the velocities of the galaxies, that would be very good, because then you really have a way to probe partially interface space. Basically, try to capture the folding in a more precise fashion. So any information which is available is useful.
I can, but I also don't want to. Okay. So, okay. Given the success of like the Zeldovich approximation, in a sense, like for megaparsec scales even today, like is there something you haven't mentioned, or something that you would think about that would be interesting to go to like a 2LPT approach then?
So at the moment we are trying to see to what scale this works, and I would have expected that it already would fail at the plot I showed, but apparently it does work. So currently we are running this now. We're trying to make this run on, for example, the TMG simulations, which have a lot more resolution, and hopefully we can then see that it fails at a certain length scale, because it would be really nice to say, well, don't trust this after this length scale. Once you have that, you can say, well, let's use second order Lagrange perturbation theory, see whether you can improve. But you can go even further, because Oliver Hahn has worked out nth order Lagrange perturbation theory, and he showed that it actually converges up to shell percent. That's exactly the point we need this. So we kind of dreaming about extending this formalism to nth order Lagrange perturbation theory, and we already have the formalism to do it, but it's just numerically challenging. But that's one thing we want to do. But it's a completely new way of studying the cosmic web. So you have a whole list of things you want to do, and based on what you see, you make a priority list. And I first thought that it would be very high on the priority list, but we have to drop it a few steps.
Because you were saying that the A2 caustic was not probed super well with just Zeldovich, right? Or
yes, so the point caustics I'm very suspicious about. So basically, so the formalism I really trust for the everything up to 4. So up to the filaments. For the clusters, I'm really suspicious the Zeldovich approximation. I have no evidence that it doesn't work, but theoretically I find it very unlikely. That's to say, basically before COVID, we had a PhD student who did a precursor of this application to the multi-core simulation that was Sibelius at the time. And he claimed, this master student claimed, that he did find a correlation between the clusters, the halos in the multi-core, in the simulation, and these point caustics. But he never really finished the project because COVID happened and he went outside of academia. So we are retracing his steps. And if he was right, then maybe you can say something with this other explanation. But before I see it, I will not.